We'll start with regularization and linear regression today. We'll firstly be looking at, okay, can you folks please settle down? Right. So we'll be starting with regularization and linear regression. We have already looked at polynomial regression, and that's what we'll start off with today as well. Let's consider this data set which I've created. This data set is something like x into sine x plus cos of 4 into x, and I've created 50 data points. I've added some random noise to the data set, and I've just done some normalization, etc., to make it appear better. I'm running this as a Streamlit app. So Streamlit app, Grad.io apps, they make it very easy to visualize various things. So this just requires Python code if you have not used them earlier. Earlier, if you had to write these things, you had to know a lot of JavaScript also, but for now you don't need to look at anything. So what you see is that you're looking at the learnt model for varying degrees. So degree 1, you learn a straight line. As I increase the complexity of the model, you can start off with the attendance sheet. So, and please don't keep the attendance sheet to yourself and sleep over it. Please pass on. If you want to sleep, just pass it and then take a nap, because last time it was very difficult. A lot of students had to wait at the end to sign their attendance. So what do you notice as I increase the degree? Right, let me go back. Okay. What do you notice as I was increasing the degree of the polynomial which I am fitting to the data? Okay, middle column, third row, anyone? Yes, middle of middle. What do you observe as I increase the degree? Yes. Okay, so as we are increasing the degree, can you see that the red line is becoming is getting closer to the blue points, right? In machine learning terms, what will you call this phenomena? The fit is improving with the increasing complexity. Right? What else do you observe? Yes, what else do we observe as we increase the complexity? It tries to make the convexity of the curve is not really convex, and we'll come into the definition of convexity if we have time. But it's fitting the data points better. That is one obvious thing that we see. What else do we see in this plot? And not just the plot, the other terms which I'm showing. So let's go over this again. Maybe just focus on the learned function, right? Sorry. So just now notice the learned function, right? So it goes from minus 0.2 plus 0.04x to 0.2 minus 0.2x plus 0.02x square to 1.2 minus 1.58x plus 0.369x square minus 0.02x cube to minus, I'm now just reading out the coefficients, minus 0.5, 2.3, minus 1.5, 0.2, minus 0.1, minus 0.1, 1.2, minus 0.6, 0.04, 1.01, minus 0.01, so on. What do you now observe? The coefficients? The coefficients of high degree terms are less, okay. That is one observation, not necessarily related to what I am trying to figure out. The value of intercept is not necessarily decreasing. The sign of what is alternating? The sign of alternate may be just some not really important phenomena, but do you observe that so let's go back. Look at just the terms. just the coefficients, 0.2 and just the absolute values for now, 0.2 and 0.05, 0.2, 0.2, 0.01, 1.2, 1.6, 0.34, and now you have terms of 2.3 minus 1.4, you have terms of 3.3, now you have terms of 3.1, you have terms of 3.5, minus 4, 17, 28, 22, 23, and now I have 60 also. So what can you see? What can you conclude from this? As you are increasing the complexity of the model, the magnitude of the degrees, magnitude of the coefficient can increase. It's generally increasing. Sometimes it may not always be absolutely increasing, but generally the trend is that the magnitudes of the coefficients and the intercept is increasing, right? And can you also observe, just look at the terms in this model. Just look at the signs. 0.9, so plus, negative, plus, minus, plus, minus, plus, minus, plus, minus, right? So both of these effects are correlated, are related. In order to compensate and in order to ensure that you're able to you're trying to get each and every point correctly, you'll have terms like plus 80x, minus 75x squared, so on and so forth, so that you can get very highly complicated varying curves and which you can model all the data. Right? So all of these phenomena are occurring together. At the same time, what can you say about the bias or the variance of the model as you increase the complexity? The variance will increase as you increase the complexity because the model is now very sophisticated. It has a lot of degrees of freedom. Right? So, can you tell me any symptom? I am asking symptoms, it is not always correct, but more or less it is correct. Can you tell me a symptom of overfitting when you are using polynomial regression like setup? So, let us go back. Do you have any overfitting here? No? What are the coefficients? What is the largest coefficient? 0.2. Do you think you have overfitting here? Right. What is the largest coefficient? So therefore, what can be a good symptom of overfitting? Large coefficients, right? And that is what we will try and look today, that we want to regularize or we want to make our models less overfit on the training data set. So we will be looking at somehow trying to reduce overfitting by not letting the magnitudes of the individual coefficients become very large. Okay. So we have seen this, the magnitudes becoming large is a symptom of overfitting, not necessarily the only symptom, but it's a symptom of overfitting which we will try and correct somehow. I've written some of the terms here, we will come to them later. So it's a symptom of overfitting because now you're trying to, so let's consider at this point, it's a very, very simple function, you don't have a lot of degrees of freedom. So therefore you will end up learning something like 0.2 plus 0.043, you have a very simple function which is trying to adjust for the entire data set, you will somehow learn the very simple mean like function. But as you increase the function, so let's say we go from, this is 3.3, let me, so in these kinds of functions, if you have to accommodate for each and every point, so for example, if you want to accommodate for this point, you will have to choose a high degree curve with a positive coefficient and another degree with a negative coefficient, so that you can bring the function down also quickly. Right? So you can also think in terms of how the Taylor series expansion is created. You can think in that terms also. You generally see this behavior as you will increase now the degree. If the data were all very nice and the data were and the function were indeed, let's say 3-dimensional, like a cubic function, and without any noise, then you will not see this behavior that much. It's just because you're trying to adjust for each and every possible data point in your training data set, some of which is noise, you will end up compensating by alternative terms of different signs in order to get more and more correctness on the training data set. Does that make sense? Sorry? So the coefficients will, if you're asking the exact mathematical reason, I also don't know that. But intuitively you can think of the purpose, you have a single purpose here. The model has a single purpose to try and reduce the mean squared error on each and every data point. Now, in order to reduce the mean squared error on each and every data point, you need a very, very flexible function. And those flexibility of the functions you will get by some, so let's say you want to get this point and this point correctly, right? So they are not exactly on a very smoothish curve, or they are on a very high degree curve. So therefore, you'll have to have a very high coefficient with a positive sign and the next one with a negative sign. That's how it will work out. If this is not clear, let me see if I can come up with a simpler explanation in the next class. Other questions on this? Okay, so thus far we said that overfitting is a problem for us. One way to measure overfitting is by looking at the coefficients. Right? So higher coefficients, higher magnitudes of coefficients means that the model has become very complex, very sophisticated, and it is trying to fit to the training data very well, which will not generalize well. So in this example, I had a different data set and I was looking at the maximum coefficient with respect to the degree of the polynomial, and I have purposefully drawn the y-axis on a logarithmic scale to show the magnitude of difference, and you can see that there is a huge magnitude of difference as we increase the degree. So what can we do to address this problem now? Goal is to reduce overfitting. One symptom of overfitting is high magnitudes. How do we reduce that overfitting? Okay. So thus far we've been dealing with unconstrained optimization. Our only objective was to fit the data as well as possible, right? As good as we can. But we've seen that if we try to fit the data as well as we can, then we may have issues like overfitting, right? So therefore, what we want to say is that let's not focus solely on fitting the data well. Let's also focus on something else. In this specific case, that something else is that we don't want the coefficients theta to be very large. We want them to be slightly small, to be a smallish number, not very large number. So therefore, you are trying to balance two effects. What are the two effects you are trying to balance out? One, you want to fit the data well. Right? Second, you don't want to fit the data too well, or you don't want overfitting, or you don't want the parameters or the vector theta to become of a very large magnitude. Right? So therefore, two effects will be, you will have a trade-off between the two effects. One, fit the data well. Second, you don't want the parameters theta to become very large. So that's the key idea. We will say that the first term is minimize y minus x theta transpose y minus x theta. This is the objective of the fitting of the data, right? This is how well you are able to fit the data. If this quantity is less, you have fitted the data very well. Plus, we want to say that we also want to minimize the theta terms, right? Now, if you want to minimize the theta term, you have various possible ways to do that. One is to minimize summation theta I squared. The second is to minimize magnitude of theta, sum of the magnitudes of theta. Right? So this particular kind of penalty which we add is the L2 penalty, or the L2 norm of theta, squared of the L2 norm of theta. Remember again that theta is a vector. Right? So what we are saying is that we want to minimize this overall quantity where we have two terms. Again, which of them is the data fit term, which represents how well you are fitting to the data? first term. And what does the second term convey? The magnitudes of the vector theta, right? So both of these effects will be traded off by this term, which is delta square, right? Who asked? Okay, right. So you have two effects at play. Firstly, you wanted to fit the data well, right? But we've seen that if we fit the data well, like in decision trees, if you do not control for depth, what happens if you fit the data well? What is the training accuracy you can get on a decision tree if you do not control for any depth? 100%. You will be able to classify or regress exactly, right? So therefore, if we have very flexible models, we'll do 100% on the training data set, but on the test data set or in general, we have poor performance, right? So that is known as overfitting or high variance. Now, high variance occurs because you fit to the data points very well. So what we're saying is that let's not fit to the data point solely. Let's fit to the data point as well as we can, as good as we can, plus we don't want the thetas to be very large. So therefore, if you want to reduce the amount of thetas, we add these two terms, loss plus penalty. So that is the general kind of expression which we get in machine learning regularization literature. Now, if you want to minimize this overall quantity, you will have to minimize these two effects in parallel, right? We will see more on this. The S. So I purposely not discussed the first variant. I have directly gone down to the second variant. Both of these objectives are the equivalent write-up. This we will consider when we study something known as KKT conditions, and then we will see that these two things are equivalent. So I specifically reserved that part for when we study support vector machines, because previously I have experienced that I introduced KKT conditions here, and then when I go on to SVM, students have forgotten it, right? So there is an equivalence between these two forms, but for now we will be only considering this form. You have the reconstruction loss or the data fit term plus some non-negative quantity, which is delta square, times the penalty term. Right. Is this becoming clear? Any question? Sorry? I couldn't get you. That second term we've got is? They both are equivalent, but of course S is not lambda square. There is some relation, but S is not exactly lambda square. We'll see this. So let's now look at the contour plots. Let's see that this star that I've marked is the solution which I would have got if I did not have any regularization, or if I did not have any penalty, or if I was not trying to control for overfitting problem. Right? This is what we've seen earlier. We have this loss surface, and using gradient descent or normal equation, we try to reach to the minima of that. Right? So this is the solution which we would have obtained if we did not have any penalty term. Right? But now we have a penalty term. So we've put penalty term of the format lambda square or delta square theta transpose theta. In a two-dimensional space, theta transpose theta you can write as theta 1 squared plus theta 2 squared. Right? So in this case, I have plotted a certain value of theta naught square plus theta 1 square, which is 3. Right? I've just plotted one value. Now what we'll do is, let's look at if, so mu here is the delta square term, which is the penalty coefficient. Right? So this is, I've kept mu to be 1, and my star is my actual solution, which I would call as my solution for the unregularized problem, or the problem where mu was 0. And my cross is the solution which I obtain when I have kept the penalty term, when I have kept my objective to be y minus x theta transpose y minus x theta plus mu times theta transpose theta. Right? So if mu is 0 or lambda square or delta square is 0, you are only looking at the data fit term or the reconstruction. Right? But if mu is non-zero, you will have to balance between these two. So what we see here is that if mu is 1, I'm saying that I'm telling you to reduce the theta terms a little, but I'm not giving it a huge importance because mu is not a huge quantity at this point, right. So therefore, the two solutions which I obtained, the star being the solution for the unregularized problem or the problem where we did not have any penalty versus the cross where I have some penalty, they are very close to each other, right. So I am solving two different optimizations and I will therefore have two different solutions. The two solutions in this case are very close to each other. Now, if you notice that my maximum coefficient is 6.49, I will just increase mu for now and we will come back to the specifics of what is happening. If I increase mu, the solution which I obtain now is further away from my actual solution or the data if I were to only fit the data. So my solution is moved slightly away, but at the same time my theta naught squared plus theta 1 squared has now reduced from 7.78 to 6.3, right. So for mu equal to 1, my theta transpose theta term, which is theta naught squared plus theta 1 squared, was 7.78. If I increase mu, my theta naught squared plus theta 1 squared terms goes to 6.3. At the same time, can you see that my black line, which is my prediction, is not as good as it was previously? Why? Because I will not fit the data as well as I was previously doing. Because now I have two terms. The competing term, which is reduce the theta transpose theta term, is now starting to dominate. Let me increase mu even further. Now mu is 1000. Theta naught squared plus theta 1 squared now becomes a very small quantity and my fit is very, very poor, right. So let's go back to this and just read lambda square or delta square and mu to be equivalent here. If mu is a very small quantity or 0, right. If mu is 0, then is my optimization the same as unregularized optimization or unconstrained optimization, which will focus only on the data fit term. If I increase mu, then this term will also start becoming big and dominating in the optimization, and this term will have lesser effect. So therefore, as a consequence of this, if mu or delta square is a very, very large quantity, you will just want to minimize this term, theta transpose theta. You will not want to worry so much about this term, right. Is this becoming clear? Sorry? Okay. So you have two terms in this expression. The first is called the data fit term or the reconstruction loss. The second is known as the penalty component. Why have we kept, so why we specifically kept this to be delta square and not delta? We just want to signify that this is a non-negative quantity, right. So penalty is always added, you don't subtract penalty, right. But in general, you can also just write this as mu or lambda and just say that lambda is greater than or equal to 0. Now, when you have two terms in an optimization, you will have to have a trade-off between these two terms. If this coefficient was 0, then the trade-off is, there is no trade-off and you are only going to be minimizing the loss corresponding to the data fit term, which means your function will fit the data as well as possible. But if you keep increasing the coefficient, this coefficient, then theta transpose theta term will start dominating in the optimization, in the loss, on the overall objective, which would consequently mean that this term has lesser of a weightage, which would consequently mean that your theta i's will start becoming small, which means that your fit will start becoming very poor, right, beyond a certain value of mu. Is that becoming clear? Other questions on this? So don't shy away if you're having questions. I'm happy to repeat. This kind of loss plus penalty you'll see in various machine learning algorithms and frameworks. Neural networks also you'll see regularization. You'll see this in support vector machines. Many times when people try to incorporate some domain knowledge, so they put something like this. This is the data fit term plus they have a penalty if you're not incorporating the domain knowledge, or you have some inconsistency with the domain knowledge. So let's say you are trying to solve a physical world problem, right? So you have some data from some sensors. You say that my reconstruction loss is my data fit term, plus you know certain physical laws. Let's say you know laws about conservation of energy, conservation of mass, etc. So those you can somehow encode in the penalty term, that those must not be violated. So if you want something to be not violated, you can keep its coefficient to be a large quantity. So therefore you will be fitting two separate terms, data fit plus some penalty term. It's a very general framework. In this specific case, we are looking at the magnitudes of theta. Any further question on this? So when we can go back to our notebook and see now what will happen. So this alpha, mu, all of them are the same terms. This alpha is the coefficient, which is the penalty coefficient. Now if I increase alpha, observe what will happen. First let me make it overfit to a large extent, and let me so alpha goes from 0.0 to 0.01. What happens? 0 to 0.01. What happens? So the earlier coefficients were 5, 24, 60, 86, 77, 45, 18, 5. Now the coefficients have gone down, right? The magnitude of the largest coefficient is now 0.98, as well as the L2 norm of the coefficients plus intercept, or theta transpose theta term, was previously 141, now it's reduced to 1.4. And can you see that we have to some extent countered the overfitting problem here? Right? We're not trying to fit to each and every data point now. By ensuring that the individual theta i's are somewhat reduced in magnitude, we can keep going further and tell me the trend that you see. Okay, sometimes some weird things happen probably because of some implementation issue. But broadly, if I increase alpha, what happens to the L2 norm of the coefficients? Can you see that there is generally a decrease, right? So which means that the data fit terms will get lesser importance in the optimization, and the penalty term will get more importance as the degree of the coefficient, as the degree of the regularization effect you are giving is increasing, right? So now if we were to go over this again, you saw that for mu equal to 1, the theta transpose theta that you got was 7.78. The fit was okay-ish. As you increased mu, theta transpose theta decreased, as well as the quality of the fit decreased. So I'm here going in the logarithmic scale, but I could have perhaps chosen a more moderate, a more reasonable value of mu, which would have fit the data well, generalized well, as well as reduced overfitting. Right? So we have something known as regularization path, which is, these are the coefficient values. This has been done on some real data set called real estate data set. As I increase the value of mu, can you see that all of the coefficients will start reducing in magnitude, right? Which is expected because theta transpose theta is what you also plus, so reconstruction or data fit term plus mu times theta transpose theta is your overall objective. If mu becomes large, the second term starts dominating. Therefore, individual theta's magnitudes will also keep getting smaller. Yes. Why? Okay, good question. The first two coefficients have increased. This seems to be violating what I just said 2 minutes earlier, or no? Do you notice that? So these 4 lines go down, which makes sense, which is as per what we have seen. But these two increase. What is going on? Okay. What is the overall objective? Y minus x theta transpose y minus x theta plus mu times theta transpose theta, right? Can you decrease theta transpose theta by increasing, let's say, theta 1 by 0.1 units and decreasing theta 2 by 0.3 units, right? Your objective is to overall reduce summation theta I squared. So, which is what is happening here. Summation theta I squared is reducing, which may look counterintuitive to say that some of the theta i's have increased, but this is possible to happen. This also happened here. For the unregularized problem, our solution is shown in the star mark. For the regularized version, can you see that the value of theta 1 is increased? It is more, so the theta 1 or the y value for the cross is more than the y value for the star. The y value for the cross, the y value for the cross is more than the y value for the star, which means theta 1 is increased, but theta naught has decreased. So, the x value for cross is less than the x value for the star. Overall, theta naught squared plus theta 1 squared has reduced, which is the main thing. We do not care about the individual theta i's, but overall we will see summation theta I squared should reduce. So, therefore, the symptom which I had mentioned at the beginning is not a very precise symptom that the magnitudes of individual theta i's have to be small or large. What you will observe is that summation theta I squared should reduce. As a consequence, more or less you will see that individual theta i's also reduce, but sometimes individual theta i's can increase. Does that clarify a question? Further questions on this? Okay. We can see the general trend that as mu is increasing, theta i's are reducing. Right? So, can we say that after a point theta i's will all become 0? As we keep increasing mu, will all of the theta i's become 0? Yes or no? At infinity, of course, but let us say that we do not have infinite precision. We have a lot of precision, but we do not have infinite precision. Sorry, we have infinite precision. So, you will see, we will see this specifically when we study lasso, which is the L1 penalty, L1 regularized linear regression. The mu, as you increase mu value, the coefficient values will keep getting smaller and smaller, but not exactly touch 0. What the consequence of that is that each feature will contribute a little bit to your overall solution, but not exactly. So, in this kind of a setup, so I was firstly using 3 decimal places here, but let us say if I were not using 3 decimal places and I were to use 10 decimal places. And let me choose a high degree. Right, so I have these high degree terms now. Now, if I increase alpha, none of the terms are exactly 0, right? They are getting very small, but none of them are exactly 0. If I had allowed alpha to become very large, so in this case alpha had kept if I allow alpha to become very large, right? Can you notice that these terms are now in the 3rd, 4th decimal digit, but they are not 0. I could have increased it much further, or let us say maybe I choose a smaller degree. These keep getting smaller, but they're not exactly 0. At this point, it's almost like a linear fit. If you want to take this further, right? So they keep getting smaller. The L2 norm of the coefficient is a very, very small quantity, but will not become exactly 0. So at this point, we have looked at that there are two different terms, the data fit term and the penalty term. Now we have to figure out the values of theta. We have to learn the values of theta given the optimization problem. So our optimization problem was minimize this overall objective, which is sum of two objectives. The first being y minus x theta transpose y minus x theta, the second being mu times theta transpose theta. If we have to minimize any objective, we can differentiate with respect to the quantity of interest, in this case theta. So we find out the gradient of this overall objective. Is the overall objective a scalar, a vector, or a matrix? It's a scalar, right? So we know how to compute the gradient of a scalar with respect to a vector theta. We have this function loss of theta comma mu. It's actually just a function of theta because mu is supposed to be fixed. We can set that to the gradient, we can set it to a 0 vector, and we do the calculation as we've done earlier, nothing new here. The only new term is the mu theta transpose theta term. If you incorporate that term, so del of del theta of mu times theta transpose theta, you'll get minus x transpose y plus x transpose x plus mu times the identity matrix. This is the new term times theta equal to 0. And if you solve for it completely, you'll get theta star theta hat equal to x transpose x plus mu I, the whole inverse x transpose y. So it's always good to verify the boundary conditions. If mu was 0, do you get the unregularized regression? Right? Unregularized regression means that there is no penalty term that you have added. So the solution there was x transpose x inverse x transpose y. And now you have a x transpose x plus mu I, the whole inverse times x transpose y. So I'm leaving the working out for you, you can figure this out later. Okay, the bias variance trade-off. If mu is 0 or close to 0, we'll have high variance. I'm talking about a high polynomial or a very flexible model. If mu is 0, we'll have high variance. If mu is very large, we'll have low variance and very high bias. We saw that. We can have a flat line being learned if mu is mu or alpha. So if we right, so we have a poor fit. Okay. Another consequence of regularization, another interpretation of regularization is that when we studied multicollinearity, which was one of the recorded lectures that I sent over the weekend, we saw that x transpose x is not invertible, or x transpose x inverse is not computable. So if a setup was like this, you can see that there is a relationship between the two rows, the two columns. The last column is 2 times the second column. So therefore, this is not a full rank matrix. X transpose x is not a full rank matrix. Therefore, this x transpose x will not be invertible, and therefore, you will not be able to solve using the normal equation method. But instead, now if we have some amount of regularization, remember the solution was x transpose x, it's not directly inverted, plus mu times identity matrix. That quantity is inverted. So if we add that small quantity to x transpose x, now is x transpose x a full rank matrix? Yes? So x transpose x becomes a full rank matrix because of this symmetry is now being broken. Symmetry as in this third column is now not the second, not 2 times the first column, because now in one of the row you have added mu, and the corresponding in the third row you have also added mu. So, the consequence of this, this is another interpretation of regularization. You have made the problem more regularized, better conditioned, better behaved, and therefore you can now solve this problem using your normal equation method also, if you add some amount of penalty term. Okay. So, often in the implementations what is done is that you do not add any penalty on the theta naught term. Right. Can anyone think of why that might be important? So, you have theta naught term which is the intercept, and you have the other terms which we generally call the coefficients. So, I am asking you a question that why might it be useful to not add any penalty on the intercept term? Okay. Okay. Okay, so somehow Jaydev has the exact same function which I am about to show in the next slide. I don't know if he's already seen it or. Let's look at these functions y equal to x and y equal to 100 plus x. These are the true functions, and we have got the data set for, we have only have 2 points for now. So, if I add a column of ones, which is I create that augmented matrix X, and then I try and compute X transpose X inverse X transpose Y. I use the regular identity matrix, and I do X transpose X plus mu I, the whole inverse times X transpose Y. So, I have kept mu to be 100. In this case, I am saying that I want the parameters theta to be very small. How am I enforcing that? How can I say that the parameters theta are likely to be very small? Because the mu value I have kept is a very high value, which means if I have two terms competing in an objective, the second term will dominate, which is mu times theta transpose theta. As a consequence, the theta hat that I learn is almost close to the 0 vector. Now, for the second data set, I do the same thing and obtain my theta hat to be 1.9 and 2.8. So far, no problem. Or does anyone see a problem? I have two different data sets. For both of them, the theta hats that I have learned are very similar. The data sets are also similar, but one of them has an offset of 100 units. Now, using these models, can you tell me the prediction for x equal to 0? You'll have to work this out in your notebooks, or you can just do this mentally. What is the prediction for x equal to 0 for the first data set and for the second data set? Doesn't need to be accurate. What is the prediction? How do you predict for any new x? X transpose theta is how you predict for an individual data point, if an individual data point is in a vector form, or in this case it's just theta naught plus theta 1 into x, right? So, for x equal to 0, what is my prediction for the first data set or the first set of parameters? So, 0.02 plus 0.046 into 0, right, which is 0.02. What is my prediction for x equal to 0 for the second data set? 1.9. Is my prediction for the first data set okayish? Not too bad, right? You would expect it to be close to 0 only. In the actual data set, it's 0. For the second one, can you see that my prediction is horrible? Why is that happening? I wanted to keep my individual theta i's small, right? I force that by design, but the true theta naught is what for this data set? 100. So, I am trying to say that don't have very high thetas. How am I enforcing that? By having a penalty term mu times theta transpose theta. So, as a consequence of that, my theta naught has become a very small value. In this case, it's become 2. As a consequence of that, when I make a prediction for x equal to 0, it comes out to be 2, right, which is exhibiting a high amount of bias. Right. So, therefore, would it make sense to do something so that I don't put any penalty on the intercept term. Right? Does it make sense? We should have had some adjustment which does not put any penalty on the intercept term. Now, question to you, how would you do that? What modification do you need to make so that you don't put any penalty on the intercept or the theta naught term? Sorry? Remove the plus mu. Okay. 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 So Jayadev has definitely looked at the slides. Okay. Just joking. So there are two ways in which we can do this. The first, we change I to an I star matrix, where we say that let's not put any penalty corresponding to the theta naught term. Right? So this specific term, the 0th entry in my identity matrix, was corresponding to the penalty for the theta naught term. And if I keep this to 0, so this is the penalty corresponding to the theta 1, this is the penalty corresponding to theta d. So therefore, the first term is the penalty corresponding to the intercept term, and if I keep that value in I, so sorry, this should be I star, to be 0, then I don't put any penalty on the intercept term. Right? So I've just modified the I to I star so that I don't have to put any penalty on the intercept term. Now, if instead of using I use I star, then the value which I learn here is theta hat equal to 1.5 and 0, and the theta hat that I learned for the second data set is 101 and something 0. Now, if I make a prediction, for the first data set I will get 1.5, for the second data set I will get 101. Right? As a consequence of this, because I have kept a very, very large value of mu, I am trying to shift all the coefficients almost close to 0. Right? If your model is heavily biased, then what do you typically learn? The mean of the data. Can you see that you have learned the mean of the data by this exercise? You have kept mu to be very, very large, which means that your model exhibits a high amount of bias, very low amount of variance. And instead of I, you are using I star, which means that you don't have any penalty on the intercept term. So therefore, your intercept learnt would be approximately equal to the mean of the data, which you can observe. Y hat of 0 is 1.49, which is a bad estimate, but not too bad. But on the second data set, you can observe that the estimate has improved significantly. Right?
Sir, why is it the mean? It should just be a horizontal line at the intercept.
So y hat is theta naught plus theta 1 into x. If theta naught is 1.5, it turns out to be theta naught plus 0 into x. Irrespective of the x, you have 1.5. So this was one specific way to do. We see that they tend towards y hat, y bar. Another way which we could have done is to ensure that we subtract the mean of the data, we make it something between, we normalize the data, or we just subtract the mean. Normalizing the data would be making the data with mean 0, standard deviation 1, or you could just demean the data or remove the mean from the data. Both of these approaches will get reasonably good accuracy. So I remove the mean from the data and I train on the new transformed y, where the mean has been removed. So the mean of the data is 101.5. I remove that and I create a new vector y dash, which is minus 0.5 and 0.5. Now on this, I don't put any penalty on my, I put penalty on both the intercept and the coefficient. And if I now look at the predictions, so I'll get my y dash hat of 0 is 0, and then if I want to get y hat of 0, I add back the mean, which turns out to be 101.5. So it's reasonably good. So we've looked at two different methods to ensure that the intercept term is also appropriately handled in regularization. Right? One is you make the data normalized, which we've seen now, and then you just learn theta independently, theta with using the regular ridge regression. This is also known as ridge regression, by the way. The second is that you, instead of using the identity matrix, you use a different version of identity matrix. I call it I star, where the first term is 0. Questions on this? Okay, how do you choose what value of mu you want to be using for the data? What penalty term do you choose? Good. So the first thing is to ensure that you understand that mu is a hyperparameter. How do you define hyperparameters? Parameters which you set before you do the learning process and which affect the overall objective, but you're not learning them. So like theta, you're learning through the objective or through the optimization, but mu you're not learning in this specific case. So therefore, mu you'll have to vary. You'll have to figure out what value of mu works best. So therefore, you can use cross validation and hyperparameter tuning to learn a good value of mu. So typically mu for hyperparameters such as the decision tree depth, you go in like 1, 2, 3, 4, 5 and integer values. For hyperparameters such as mu, you typically go in the log scale. 10 to the power minus 3, 10 to the power minus 2, 10 to the power minus 1, so on and so forth. And typically you don't choose very high values. So this is just regular cross validation. Now you can also solve the ridge objective using gradient descent, right? Because you have solved it using normal equation. You can also use gradient descent like procedures for such optimization problems. Your updated value of theta is the old value of theta minus alpha. Here alpha is the learning rate times the gradient with respect to the overall objective. The overall objective is the same as what we wrote before. If you just solve it for a few more steps, you will get an expression which is theta equal to 1 minus 2 alpha mu I times theta minus alpha times this expression. If we did not have the regularization term or mu was 0, both of which are equivalent, which is unregularized regression, we'd get the update rule as theta equal to theta minus alpha times minus 2x transpose y plus 2x transpose x theta. Right. Can you notice that as a consequence of the new term that you have added, which is minus 2 alpha mu into the identity matrix, you have two terms in this theta update. The first one is shrinking theta, the second one is just doing the regular update, right. So if you had unregularized regression, you had new value of theta equal to previous value of theta minus alpha times the gradient, whereas gradient of the data fit term, right. So this is the gradient of the data fit term, whereas if you have ridge regression or if you have L2 regularized linear regression via gradient descent, if you are trying to solve, you get new value of theta equal to old value of theta scaled down by some factor, which is a function of mu minus alpha times the gradient of the data fit term, right. So you have two terms as before. In unregularized there is no shrinkage, in this is shrinkage. You can also understand this geometrically. So let's say this is unregularized linear regression. You had theta at some iteration t in some 2-dimensional space I have drawn, but this could be in any d-dimensional space. I find out the gradient of the objective or only of the data fit term, which is residual sum of squares. So all of these terms are used interchangeably. Residual sum of squares, mean squared error, and summation epsilon I squared or y minus x theta transpose times y minus x theta, and you obtain the gradient of that with respect to theta at theta t, at the current iteration theta t. You subtract that, right, and multiply that with alpha, of course. Then you get a new vector theta at iteration t plus 1. Right. So through this geometric drawing, we can understand the vector way of how gradient descent works. You have theta at some iteration t, you have alpha times the negative gradient of the objective. You do a vector sum of these, you get the theta at the iteration t plus 1. This is unregularized regression. In regularized regression or ridge regression, L2 regularized linear regression, everything is the same. You start with theta t, but then you scale down theta t by a factor of 1 minus 2 alpha mu I. Right? So, you have scaled it down, as a consequence of which now if you notice the theta t plus 1 which you obtain would be always lesser in its L2 norm compared to if you were not using regularization. This is a very important result to see. So, as a consequence of this, we have seen that when you apply any amount of regularization, the magnitude of the theta vector which you obtain or the L2 norm of the theta vector which you obtain would always be lesser or equal to the magnitude of the unregularized case. Because we are observing that also, that we have a shrinkage corresponding to this 1 minus 2 alpha mu I term, and then there is a gradient update. Any further questions in this? This one? Alpha is the learning rate of gradient descent. Mu is the penalty coefficient that you've kept. So often, sometimes when people try to solve them and they're just using vanilla gradient descent and they're not using more sophisticated optimizers like Adam, etc., then you have two hyperparameters, mu and alpha, and you're trying to figure out the best amongst both of them. How much energy do you folks have? Based on that, I can choose whether to teach convexity or to teach another form of regression. I don't sense much energy. Are you folks too tired after the games last night? Everyone participating? Okay, we will not be able to complete. Let's see. How many of you know what is a convex function? Okay, at least the folks. Can someone define what is a convex function? Sorry? Okay. Okay, it seems some of you know the definition of convexity, so I'll perhaps keep this in some tutorial and I'll go on to the discussion on lasso regression. So the purpose I teach convexity in this lecture is that the sum of squared errors or the residual sum of squared errors or the y minus x theta transpose y minus x theta term, that is a convex function. Convex function have a single unique minima, which is the local or the global minima the same. The second term in the ridge regression was theta transpose theta, which is also a convex function. It's a y equal to x square like term. If you add two convex functions, you get another convex function. So this I was showing that if you use gradient descent to solve the ridge objective, you are guaranteed to get the single optima, global optima. Similarly, in the case of lasso regression also we'll see. So lasso is known as least absolute shrinkage and selection operator. We'll see the different terms which occur here. Least absolute, what do you think least absolute means? So ridge regression uses the L2 penalty, right? L2 penalty is summation theta I squared. What is the L1 penalty? What is the form of L1 penalty? Summation of modulus of theta i's, right? Modulus means least absolute, and you're trying to minimize it. So absolute values, this is indicating that this is trying to solve the N1 penalty form. Second, there is a shrinkage. So we saw that the values of theta i's were reducing, or the magnitudes of theta i's in some extent were to some degree were reducing. Actually, their L2 norm was reducing, but in this case, you'll see the L1 norm to reduce. So that explains the shrinkage component. Then there is a selection operator. What do you think that means? Let's say we want to predict the energy consumption of this room. You tell me if some of the features, you would want to select them as important features or not, or relevant features or not. One of the features that I give you is the number of participants in one number of students. Is that important to energy consumption? Let's assume that the AAC works based on the amount of CO2 and it is important. So I'm forcing this to be important. Is it important to know the number of people who are wearing smartwatches? No? So perhaps you don't know that, or you're not from the domain. You'll want a machine learning model to automatically figure out which of the features are important and which of the features are not important. So perhaps if an individual theta I, or the coefficient of an individual feature, turns out to be 0, exactly 0, not close to 0, exactly 0, can you conclude that the feature is more or less not important? Right? So that is what we hope to do via lasso regression. So therefore, as a consequence, you'll see that individual theta i's will become exactly 0 in lasso. In L2 or ridge regression, they didn't become exactly 0, they became very small but close to 0. Can you please close the laptop? So the only change which we have in this formulation is that previously we had y minus x theta transpose y minus x theta plus mu times the L2 penalty with the L2 norm of theta, and now we have the L1 norm of theta. Right? So it's fairly similar. The first term is a convex function, the second term is also a convex function. We'll discuss more in the tutorial if needed. So therefore, the overall term is also a convex function, which means it has a single unique minima. But we have a problem here, which we didn't have for the L2 norm or the L2 regularized ridge regression. Is modulus of theta differentiable? Or the L1 penalty, L1 norm of theta differentiable? Is y equal to mod x differentiable? No? So then what do we do? How do we solve this problem? Thus far we'd been very happy, right, that whatever you do, you just give me some objective function, which is some loss plus some penalty, and I'll just give it to gradient descent. But now if I cannot compute the gradient, I am doomed. What do we do? What can we do? You can compute the gradients at all points except for one point, except for 0. But it's not a differentiable function everywhere. So a lot of numerical packages, so they will just say the gradient to be 0 or 1 and it doesn't really matter. That's one way to solve it. If I am using some automatic gradient package, think of this as at x close to 0, if you put a gradient of 0 or a 1, it doesn't really matter, because x is so small. Right? But correspondingly, we'll see that there are better methods to solve it, and there is another different concept known as subgradient. When we cannot compute the gradient, we can still compute something known as a subgradient. We'll end up using an optimization algorithm called coordinate descent, which if you just thought about the meaning, so it will look at different coordinates or different dimensions, and it will do descent across one of them at a time. Previously, we were seeing circles or hyperspheres, right, corresponding to theta is squared. Now we have magnitude of theta naught plus magnitude of theta 1, so on and so forth, equal to some constant. Can you see that these will be rhombus or diamond like shapes? Sorry, not rhombus, diamond like shapes. And as a consequence, you will see that as I will increase mu, so mu will go from 1.25, you will see that magnitude of theta naught plus magnitude of theta 1 should reduce. Right? Can you see that it reduces? It goes from 6.22. Now, if mu is 1.5, it goes to 5.97. 1.75 it goes to 5.94. At mu 2, it goes to 5.92 and so on. But one interesting thing is that what is the value of theta naught that we have obtained currently? What is the value of theta naught at the cross, at the lasso solution? Exactly 0. Right? So, it was not exactly 0 at this point at when mu was 1.5, 1.25, but as soon as we had mu equal to 1.5, the value of theta naught has become exactly 0, right? Which means that we have selected out the intercept term in this case. This was not happening previously when we were discussing ridge regression. We had values which were becoming very, very close to 0, but not exactly 0. So, there was no selection as such happening, but now we are seeing the selection is happening. So, this also means that lasso often gives us sparsity. So, it gives us sparsity in terms of the number of features which you use for final prediction. Right? Let us say that you are constrained by running this model on a very small device. Let us say a very small microcontroller. So, you can't do summation xi into theta I for a lot of theta i's, you can't do that. But if many of them are 0, right, you have a lot of sparsity in your theta space, which means that a lot of features are not used. So, therefore, lasso gives you sparsity, lasso or L1 regularized linear regression. Now, there are two variants, two ways of understanding the sparsity that you get via lasso. Both of them are a little ad hoc. So, don't expect rigorous analytical guarantees for the things I am presenting. These are just very simple intuitions to help you understand that why with L2 penalty you don't get exactly 0 for some features, whereas for L1 you will get that. So, here I have plotted the unconstrained solution. The solution, if you did not have any penalty, it would have been the midpoint, the middle of this centroids, and this is the overall constrained solution which I am obtaining, right, which is when I am looking at both the terms, the data fit term plus the theta transpose theta term. I do the same for L2, L1 and some LP norm when P is between 0 and 1. Now, as you notice that as we are moving from left to right, the sparsity generally increases. Can you also notice that the probability of intersecting the axis is also increasing? Right? So, look at the surface area this has except for the axis points. Right? So, think of this as if you have a stone, so you have a balloon, let us say. So, these things, the data fit loss functions, let us think of them as balloons. You want to burst a balloon. If you want to burst a balloon, would you use a stone, would you use a diamond, or would you use a diamond which is in this shape? Which of them is more likely to burst the balloon? So, you can see that as you move from left to right, the probability of intersecting the axis increases, which is the same as the balloon example. You are much more likely to hit this, these two surfaces will intersect much more likely at some particular axis, right. In the case of the circle, like there is a lot of surface area here. So, you have a lot of points at which these two curves can intersect, whereas for these two cases, it gets more pointier. So, therefore, the probability of intersecting on one of the axes is increasing. In this case, it's very, if you decrease P a lot, you have a lot of surface area available, like the probability of intersecting is very, very high at the axis points. So, as a consequence of this, we can see that there are more solutions, there is more probability of getting some individual thetas to be exactly 0 for L1 norm as opposed to L2 norm, and as increase the norm, as it decrease the norm, this increases further. But as I mentioned, this is a very, very rough, very ad hoc, very hand wavy solution, intuition to give. And you also notice that as we move from L2 to L1 to LP, the optimization becomes harder. L2 optimization we have already seen, we can directly just use your gradient descent. L1 we have non-differentiability, and LP introduces more kinds of challenges. Fun question, I won't ask in the exam, or maybe I'll ask in the exam. To think about what happens for the what is the L0 and the L infinity norms. Just look at L0 and L infinity norms. The second intuition is somewhat easier to understand, but again it's a ad hoc intuition. So let's say that we have y equal to modulus of theta and y equal to theta square by 2. I want to obtain the minimum of these functions via gradient descent. I have started with theta equal to 5 in both the cases. So I have theta equal to 5, correspondingly y equal to 5, and theta equal to 5, correspondingly y equal to 25 by 2. I'll just assume for the first case that I am dealing in the zone where theta is greater than 0. So therefore my derivative with respect to theta, del y by del theta is 1. In the second case, del y by del theta equal to 2 theta by 2 is theta. Now, my first update to theta is theta minus, let's say my step rate is 0.5 or my learning rate is 0.5 step size. So my new theta is theta naught minus 0.5 into 1, because my gradient which I obtained was 1. So therefore I move from 5 to 4.5, whereas in the other case I moved from theta naught equal to theta naught minus 0.5 into del y by del theta, which is theta. So I moved from 5 to 2.5. Which of them is going to get you closer to 0 quicker? In the second one, you have moved from 5 to 2.5. In the first one, you have moved from 5 to 4.5. Which of them gets you quicker to 0? Second one, right? How many think it's second one? So this was supposed to be a trick question. So in the first iteration, you moved from 5 to 2.5. You moved a big deal, but the movement was proportional to theta. In the second case, the reduction that you have in theta is a constant. So therefore, if you do this for more iterations, you go from 4.5 to 4.0, whereas in this case you move from 2.5 to 1.25. So you can notice that we are halving each time. And here we are reducing by, in the first case we are reducing by 0.5, in the second case we are halving each time. We move, so we can generally write this recurrence that the new value of theta at t is the older value of theta minus 0.5, and in this case it's 0.5 times. If I do this for 10 iterations, in the first case I'll get theta equal to exactly 0. In the second case I'll get 0.0048. In the next iteration I'll get 0.0024, 0.0012, so on and so forth. Will it exactly touch 0? No. So this is the other way, other intuition of understanding why we don't exactly get zeros for individual thetas for L2, whereas we get it for L1. So therefore L1 or lasso gives you feature selection, whereas L2 does not exactly give you feature selection. Makes them very, very small. You can threshold them if you want to, but that also has some issues. Yes. Yeah, so you can keep on oscillating, but as I was mentioning, this is a very ad hoc example. This was a very ad hoc example to just force the behavior that you can reach zeros, I mean with appropriate conditions, whereas in the other case, you will not be able to reach. You will get something very, very small. You will need infinite iterations to be precisely 0 mathematically. Assume step size to be a small number. If step size is reasonably small, you forget about the divergences, you should be able to reach in a constant rate. So don't try and don't worry too much about the the rigor of